Welcome to the Future Tech edition of the Finding Genius podcast. Forget frequently asked questions, forget common sense, common knowledge, or Googling for information. How about advice from a genius in their field instead? 95% of people in any profession are good enough to be qualified and licensed. 5% go above and beyond. They become very good at what they do, but only 0.1% are the geniuses of their profession. Richard has made it his life's mission to interview the geniuses of their fields in areas such as AI, 3D printing, quantum computing, blockchain and Bitcoin, and more. Don't miss out on amazing podcasts with geniuses. Review us on iTunes or wherever you listen, and go to futuretech.findinggeniuspodcast.com and subscribe today.
Hello, this is Richard Jacobs with the Finding Genius podcast, Future Tech Edition. I have Dr. Itamar Sivan. He's the co-founder of Quantum Machines, and we're going to be talking about a whole range of incredible quantum technologies, including superconducting qubits, nanowires, quantum optics, atomic clocks, etc. I don't know how much of an understanding we'll get, because I'm sure these are complicated things, but it'll be fascinating to talk about them. So, Itamar, thanks for coming. How are you doing?
Doing good. It's my pleasure, Richard, to do this session with you.
Well, great. Tell me a little bit about your background. How did you enter into the world of working with quantum systems and actually capitalizing on them to make machines and useful things from them?
Yeah, sure. So basically, my background is mostly to do with quantum systems. So just going through it chronologically. So my master thesis already, which I did in Oxford University, was in quantum optics and physics of cold atoms, which has much applications today in quantum computing. And in my PhD, I worked on quantum electronics and what we call topological quantum computing. So basically most of my background is quantum, quantum physics, quantum computing, and these sort of things. And also in my background, so I also founded and managed the entrepreneurship program of the Weizmann Institute. That's where I did my PhD. So in a way, answering your question in full. So my background contains quantum computing and entrepreneurship. So then there you go. What else could I do but found a quantum computing startup, right?
Do you have a pretty coherent background in the quantum world, right? Bad joke. Well, okay. Out of the quantum machines in your bio, okay, so I see things like, superconducting qubits, nanowires, quantum optics, etc., atomic clocks. Which of these things would be the easiest to start the discussion, for a lay person to get a grasp on how they work and what the item is trying to do?
So maybe I didn't work on the entire list, but maybe this list is of the things that, the founding team of QM have worked on. Well,
let's pick instead. What are you working on right now that you're just having a great time and working on? What's your project right now? Your main project that you're in charge of that is really fascinating you. Let's get into the facets of it.
So basically, at QM we develop what we call the quantum orchestration platform, which is a hardware and software system that allows to run extremely complex algorithms on quantum processors. That's the major thing that we're doing here at the company. And one of the interesting things is that even though we could kind of take a deep dive into a particular quantum system and talk about its bits and bytes, the platform that we're developing over here is in fact agnostic to the quantum, to the quantum device. And in fact, the technology can be leveraged to running algorithms on pretty much any quantum processor, or by the way, quantum system. And that's mostly what we're doing.
So what's special or necessary about software that runs quantum systems versus traditional classical systems?
So Okay, so that's a great question. So first of all, I think that the most important thing to stress is kind of the stack of the quantum computer, okay? Which is very, very different from a classical computer, okay? So a classical computer is I'm sure you and your audience know, you can break it down very, very roughly into two layers. That's enough, which are the hardware and the software, okay? And that's different in the following sense from a quantum computer, which is you can regard the stack as having three main layers, which is quantum hardware, classical hardware, and software. Okay, so fundamentally in a quantum computer we have three layers, and what we develop here at QM is the classical hardware layer and the software layer of the quantum computers, of quantum computers. And that is essential because the quantum layer of the quantum computer, which is, it's the heart of the quantum computer, of course. One of the most interesting things about it is that it contains all the quantum information or the quantum data, but it doesn't contain the logics of the computer, but rather the logics or the algorithmics of the computer are controlled or orchestrated from classical systems, from classical hardware and classical software. And that's something very, very important, which is also the reason why we started the company.
Yeah, I know at some point we'll run into proprietary things you can't say. That's okay. But just let me know what you can say. So how does a quantum computer work? How would you describe it?
How does a quantum computer work in general?
Yeah, maybe one of the particular flavors of computer that you're developing, algorithms and software for. Like what insights do you have on how it works differently from a classic computer?
Cool. So in fact, in order to explain how a quantum computer fundamentally works, we don't even need to go into a specific implementation of a quantum computer. I think that the most interesting part is the concept of how it works in general, okay? And the concept of the quantum computer is based on what we call the quantum bits, okay? And the quantum bits are the fundamental building blocks of the quantum computer, and they differ from the bits, the classical bits, which are the fundamental building block of classical computers, in the sense then that while classical bits can be 0 and 1, quantum bits can be in both 0 and 1 at the same time, okay? So classical bits, again, any information that you have on your computer, whether it is, some Word file or some photograph, whatever, it's all maintained, it's all saved with classical bits, okay? Even a photo that you take, you take a selfie with your phone, then eventually it is saved with zeros and ones. Yeah, maybe it is encoded, you take a photo, then it's 000111000. Yeah, that's how it's saved eventually on your phone. But in a quantum computer, you have something very different, which is quantum bits, which can always be in 0 and 1 at the same time. And this fundamental thing may sound as a detail, but it makes the whole difference, okay? And the way it works is that, if you have a single quantum bit, then as I said, it can be in 0 and 1 at the same time, okay? And then if you have many quantum bits, in fact, they can be in all of the different combinations of zeros and ones at the same time, okay? Let me explain, okay? So for example, let's say you have 3 classical bits, okay? In a classical computer. Now, they can be in certain combinations, right? They can be 000, maybe they can be 111, 011, 110, and so on and so forth, right? If you now have 3 quantum bits in your quantum computer, then they can be in all of these combinations at the same time. And that already makes a difference, because, for example, if you have now 300 classical bits, okay, then the number of binary combinations you can place them at is 2 to the power of 300, okay?
The power of a quantum computer grows with 2 to the n, and n is the number of qubits.
Exactly. Now, 2 to the power of 300 may sound, not too big, yeah? But in fact, 2 to the power of 300 is more than the number of atoms in the universe. Huge number. Yeah. So I'm telling you, if you have a quantum processor with only 300 qubits, quantum bits, it can be in more combinations, binary combinations, than the number of atoms in the universe at a single point of time. Yeah. And this is fundamentally what we leverage for getting this immense computational power that quantum computers, may unlock.
What's the state of the art right now? I mean, I don't know if there's any real 300 qubit machines, but
There isn't
I've heard
any.
about 50, maybe.
There isn't any. There isn't any. That's a good question. So today, the leading teams at some of the multinationals like Google and IBM, they're making huge efforts and huge progress. They have amazing teams, and they have now some 50 qubits processors. So IBM declared their 50 plus qubit processor. Google declared their 70 plus qubit processor. These guys are advancing pretty rapidly. And we do anticipate that the numbers will grow since they're putting more and more resources into the field. And you see new players going into the field, like Amazon, for example. And of course, there's Microsoft, which are highly involved. And going back to the previous point, you see, since this is an exponential process, then, for example, if we go from 50 to 100, this is not twice. This is much more. Yeah, this is two to the power of 50. Yeah, just to give you a sense, for example, 2 to the power of 60 is more transistors than you have, more than the number of transistors you have on Earth.
Wow. Okay. So what's the focus right now? Is it to make a more robust, 50 qubit machine, or is it just this race for the sake of more qubits, stable or not stable?
The race is now on multiple axes. The main race is on expanding the quantum processors for them to be bigger and more stable. And I'll make it clear. So the holy grail of quantum computers is thousands of extremely stable, let's call it flawless, or as we call it technically, fault-tolerant quantum bits. So thousands of fault-tolerant quantum bits, okay, which we call it, this is what we would call a fault-tolerant quantum computer. This is the holy grail.
In a quantum computer, is each qubit physically somehow isolated from the others, or do you have a system where you have, I don't know, all the qubits in the same area that are all, undergoing quantum effects at the same time? Like, what would the system look like? Would it be a honeycomb of individual qubits housed separately, isolated each?
So that's a good question. And in fact, the qubits must be in the proximity of one another. They cannot be isolated from one another because you need them to interact. You cannot get the computational power if they do not interact. Okay. But this is also, why is it a good question? Because this is also the challenge. Okay. Because once you put them one next to the other, the system becomes noisier and harder to control. Yeah. And so this is kind of this is the biggest challenge. So, for example, the biggest challenge is that there is a very, very high error rate. Errors occur very, very rapidly in quantum processors, okay, to quantum bits. Now, in theory, you could do what you suggested, okay, which is completely isolate qubits, yeah. But once they're completely isolated, you cannot run algorithms on them, yeah, and you cannot couple them to other qubits. And that's kind of the paradox. Yeah, on the one hand, you want them to be fully isolated. On the second hand, you want them to be highly coupled and close to one another. So Google, for example, had some nice breakthroughs in this venue, which is what they call dynamic decoupling, and others are pursuing that as well, which is simply kind of controlling. You let them be isolated when you don't run any operations on them, but you let them be connected when you want to run operations on them. Yeah, you do it dynamically. So, for example, now I want to run an operation on two of my qubits. Then I let them be in interaction. Then I operate them, and then I dynamically stop the interaction.
So what are you using to make, well, not you, but what do companies use to make qubits? Are they atoms? Are they electrons? And what are they using about them? What's the entanglement? Is it the spin? Is it, I mean, some of the fundamentals. How does a qubit work?
Yeah. So the thing is that there are many different implementations for qubits. Like there isn't yet what we call, the silicon transistors of classical processing. Yeah. In classical computers, the majority, is based on silicon transistors, right? But we don't have such a platform which is known to be the leading platform for future quantum computers, but rather there are many proposals. So the one who is leading today is, for example, superconducting qubits, which is based on aluminum. These are microcircuits which are fabricated with lithography based on aluminum. There are other implementations, for example, trapping single atoms. So, for example, if you take, so you need to imagine this. So if you imagine, for example, a small vacuum chamber, okay, like a size of 30 centimeters on 30 centimeters, okay, on 30 centimeters, and inside you place, you have a laser, okay, a laser beam, and the laser beam would then trap, for example, 20 single atoms, let's say ytterbium atoms or rubidium atoms, which are then in vacuum trapped one next to the other in a row, okay? So then you have these 20 atoms in vacuum trapped one next to the other, and then you employ each of them as a qubit, yeah? So this is an example. And for example, and then you have, you also have ones which are based on silicon, and also ones which are based on diamonds, so defects, single atom defects in diamonds, and so on. And in the nice thing is that they always need to be maintained in some extreme conditions. Okay, so for example, you need to have extremely high vacuum in the case of these trapped atoms that I mentioned, or for example, the implementations that rely on silicon or on aluminum. They need to be in very, very low temperatures, so 10 millikelvin above the absolute zero. So that would be like in Celsius, more or less, minus 273 degrees. So extreme conditions they have to suffer.
Okay, I gotcha. So what are some of the trade-offs between the different systems that you see out there? Are there pretty significant ones? As you said, everyone's trying to find an ideal or a systematized implementation of a qubit. But are you seeing some are a lot more robust than others, or what's the standard right now?
So most of the trade-offs are to do with, in fact, what we discussed earlier, which is the trade-off between how isolated the qubits are and how easy it is to interact with them. Okay, so for example, you have some implementations which have very, very good isolation and therefore a much lower error rate, but on the other hand, it takes much more time to interact with the qubits. So this is one type of trade-offs, and the other one is, of course, scalability. So maybe you can have a very, very good 200 qubit processor, so no one has it now, but maybe in 2 years or even less. But then the next question would be, okay, how do we scale it up to 2,000 or 20,000 later on? So these are the main differentiators between these implementations.
How much time do you have to perform a calculation? I would think that time is of the essence, and it's very difficult to keep, the qubits in the state needed to do a calculation.
Oh yeah. So, for example, if we talk about what we call superconducting qubits, which are those qubits based on aluminum, and which are pursued by most of the companies, I could say. So these qubits, the information within them live for let's say, hundreds of microseconds, maybe a millisecond, depends on how many qubits you have in the processor. And this is, as you said, this is the time, this is your time window for running the algorithm. So within these hundreds of microseconds, you need to finish everything. Yeah.
So I'm not sure if I'm going to say this right, but if you have a lot of qubits and you want to do a massive calculation, I would guess you'd have to keep the initial data set, in classical circuitry, feed it into the qubit system, get, the answers out and put it back into the classical circuitry. Is there any problem in storing the amount of data needed, or, the in and out of interacting with the qubits? Is it easy to put the data in to start the calculation, but hard to get it out, or vice versa?
So generally speaking, this is a big challenge. And I think that the fundamentally this challenge comes from the fact that, as we said earlier, there is an exponential difference in complexity between the quantum system and the classical system that needs to operate it, or as you say, it needs to send data, it needs to get data, and so on and so forth. Yes. So just, going back to the numbers we had previously. So for example, if you have 300 qubits, then you would need, or let's take even a small number. If you have 70 qubits in your processor, there's no computer on Earth that would be able to describe this amount of information ever. There's not going to be such a computer ever. So fundamentally, this is a huge challenge. You're running an algorithm on a processor that you cannot even describe on your classical machines the information you load into it, or you get from it. Yeah. It induces many additional challenges, like verification of quantum processors. So for example, let's say you ran an algorithm, okay? You get a result. Is it easy to verify that the result is correct? In many cases, no. Yeah, because you couldn't solve it with a different system, so you cannot make sure it's correct. Yeah.
Where do errors come from? What does an error look like?
So the errors come from interactions with the qubits with one another and with their environment. So the thing is that qubits are extremely fragile. One of the most famous examples is to use the analog of let's say a coin. Okay. So a classical bit, you can think of it as, so we said it's either 0 or 1. You can think of it as a coin that you put on your table. Okay, so you put it on the table, you put it face up, and it's not so susceptible, right? I mean, even if you kind of jump on the table, it is not likely to flip, right? But then, for example, imagine that you're taking this coin and you're putting it in air. Okay, like floating in air, okay? Now you can imagine that even if there is the slightest wind next to it, it will start diverging, right, from its initial position.
Right.
Right?
Like if it's on its edge, you say, is it head or tails, where it's kind of both until it moves in one direction.
Exactly. If it's held in air, there's gravity does not force it to be, on one side. Then it's enough that there's a little bit of, wind next to it, and, it just starts, it gets a slight angle. Yeah. And this angle is an error. For example, I put it in a certain direction, like face up, and then, there's a slight wind and it starts diverging just by one angle. This one angle, one degree. Yeah, this 1 degree could be a complete loss of information. Yes. And this is exactly the problem with quantum bits. This is the analog to quantum bits. The quantum bits are in fact analog. Yes, they don't have to be either 0 or 1. They can be in any angle. So they're very susceptible to small things happening next to them. And these small things are in fact electromagnetic waves. So typically RF, radio frequency radiation next to them, which causes them to diverge from their initial position, or wanted position, and basically causing errors.
So if I have a 50 qubit machine, why can't I have a 51 qubit one or 101? Like, why is there? Is there a different complexity in just having one more qubit or two more when you're at a stage of where you have 50 or 100 of them?
So you can, you can, if you do, you can add them. Yeah, you can, if you have a silicon substrate and you put little qubits from aluminum on it, you can put thousands, yes? But each one of them adds more noise to the system, this kind of RF noise, electromagnetic radiation noise. They interact with each other, which is causing additional errors. And so it is, in fact, every bit is challenging.
Yeah, are there certain numbers of qubits that are more stable than others? Like, I've never heard of an 89 qubit machine or a 33 qubit machine. Are there certain even numbers are better, or, are there ranges of qubits for some reason that are problematic? Let's say like the 60 to 75 range for some reason is just unstable, and then it gets stable again once you get to 80 and beyond. Does any of that happen?
Not that I know of.
Okay. When you speak to companies, do they tell you, well, we have a 94 to 110 qubit machine, but it depends on the day, or they just give you one number? I guess it's just a strange question, but the idea.
No, it's a good question. But the answer is that they have many. They have many types, because even those who have tens of qubits, they have systems with maybe 10, and systems with maybe even just one, because they investigate them. They investigate 2 qubit systems in order to then later implement them into the bigger ones. Yeah. So. Okay,
gotcha.
Yeah.
Are there certain geometries that seem to be favorable, or arrangements? Once you get up into the 10 qubits and above, are there certain geometries that work better for stability versus 50 qubits or 100?
Yeah, that's a good question, and there are many architectures. The geometry is part of the architecture, and there are many different architectures. I don't think I can say which, if there's a good architecture, each one, each company or each team is pursuing a different geometry and architecture. So maybe in 10 years we'll be able to answer.
1 second. So what are some of the elements that you're trying to optimize about, and improve about quantum computers, specifically at QM?
So basically, so you see, you have the quantum processors, which have this promise for immense computational power. But in order to realize their potential, you need extremely advanced classical systems. And for example, even today you have quantum processors, as we said earlier, but even today we cannot realize the potential of the quantum processors that there are. Yeah, say for example, you have a 30 qubit processor. Even today, you cannot realize their potential, its potential, okay? And we provide systems that allows anyone who is developing quantum processors to realize their potential of their quantum processor, whether they have, 2 qubits, they have 20, and even when they will have 200.
Yeah, when a company says right now, oh, we have a 50 qubit machine, does that mean they're really getting that much performance out of it, or is it very inefficient?
No, when the companies say they have 50 qubit machine, they have 50 qubit machine, which is working very, very nicely. As I said in the beginning, all of the big teams are advancing at an extremely fast pace and doing an amazing job. But there is no doubt that there are many. Every layer in the stack, if you improve it, can allow you to do more. Yeah. So we provide the classical systems that allow you to do more with any quantum processor that you may have.
And what are some of the problems that you think quantum computers will be uniquely identified or able to solve?
That our system is allowed to solve? Or that quantum computers in general will allow to solve?
First in general, and then with your specific improvements in implementation, I guess same problems, just better. But what problems in general do quantum computers look like they'll be better to solve?
So that's a good question, and not an easy one, because there's the question of not only what but also when. And the thing is that, quantum computers will begin being useful hopefully in the next couple of years, and they will start impacting some industries through, running some algorithms extremely fast. And then farther down the line, the scope of algorithms that they will be able to run will become wider and wider. So on the short term, things like simulations of molecular processors or chemical processes will likely be run very efficiently, very well by quantum computers once we reach the few hundreds of qubits in a quantum computer. And on the longer run, the scope of things that will be run by quantum computers one can only imagine. It would be probably immense. As an example, so one of the promises is that quantum computers may impact things like machine learning and AI. Yeah, because there are many algorithmics that we use very often in machine learning that could theoretically be run extremely faster on quantum computers. And so in a few years' time, I believe that over there in machine learning applications, the biggest disruption will arrive.
Yeah, other systems that you think quantum computers will be really good at modeling? You mentioned it briefly, but what are maybe the top 2 or 3 that you think will achieve breakthroughs? What are some of the top problems that we're going to see breakthroughs in the near future due to quantum computing, do you think?
So I think that so I wouldn't name problems. Yeah, I mean, I wouldn't name specific problems because no computer is made for a specific problem. Yeah, I mean, for example, today there is a huge trend of developing processors which are tailor-made for AI, right? But these processors are not developed for a particular problem, but normally it would be what we normally refer to it as a class of algorithms. Yes. So I'd say that the class of algorithms of molecular and chemical processors and simulations, these things could disrupt fields like pharma or the development of solar cells and so on and so forth. And then I think it's pretty well established that quantum computers could disrupt financial markets, financial modeling, and so on and so forth. There could be huge impact over there. And then I really think that sometimes people list industries that could be influenced, but it's not like anyone went through particular all of these industries and said, okay, here we can disrupt it, here we can disrupt it. It's simply because there are particular algorithms or particular subroutines or mathematical operations that we could run much faster on quantum computers, so that any industry or any market that is relying on these algorithms and subroutines can benefit from quantum computing. And therefore, I think that the main conclusion is that quantum computers could disrupt almost any industry, and it's all a question of when.
Yeah, what's your sense of when? I know there's multiple companies working on quantum computers, but do you feel like breakthroughs are close, or it's still going to be quite a while?
I think breakthroughs are close. I think that in few years, maybe 2-3 years, we're going to see the first useful algorithms running on quantum computers. And this will be the beginning of a new era, because once we see useful algorithms running on the quantum computer, then this will lead to even more resources going into the field and even a faster progress. But I'd say that it would start in very few years, 2-3 years, and from there, the sky's the limit.
What about for everyday applications? I have my smartphone. It uses, cloud computing, classical computing. At what point what size of a system do you think would be necessary or useful for an everyday user so they get utility from it? It doesn't have to be tons of qubits, but is a product like that you think going to be available soon?
So I don't think there's going to be a quantum processor in your phone, in any time in the foreseeable future. But I think that people will benefit from it in indirect ways. So I'll answer it in two ways. So first of all, if pharma companies have quantum computers that for their use, then they can develop new drugs, better drugs that anyone can then use, right? It will be in the benefit for the entire society. The other thing is that there are many things in your day-to-day life that you do which require, for example, extremely heavy computational heavy lifting, and you don't really know it. For example, when you're using Facebook, Facebook is using immense computational power for AI engines that they're using to optimize things for you, right? So does Google, and many of the companies that you use their products on a daily basis. So once we get quantum computers that are capable of doing this heavy lifting, then let's say starting in 5 years and on, then you will benefit from it in indirect ways, because these companies are going to use these computers to optimize things for you.
Well, very good. Itamar, what's the best way for people to find out more about QM and your work then?
So I, of course, welcome people to reach out. People can contact us through our website. There is some information on the website, but again, people are welcome to reach out, and we're always happy to schedule meetings and educate people about quantum computing and the upcoming revolution of quantum computing. We see it as part of our mission, and also in the upcoming months, we'll add more and more information to our website. We'll add more tutorials about our quantum computing programming language and the programming interface, and broadly about the quantum orchestration platform.
Well, very good. Well, I appreciate you coming. It's been a good call, and I know I asked a lot of difficult questions, but you handled them well, so thank you.
Thank you very much, Richard. My pleasure.
You've been listening to the Future Tech edition of the Finding Genius podcast. This podcast is information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed. Review us on iTunes or wherever you listen, and subscribe today by going to futuretech.findinggeniuspodcast.com.